Hello everyone, hope you all are doing well. In this lecture, I am going to discuss particularly about control for deflection under limit state of serviceability. Okay, so limit state of serviceability relates to the performance or the behavior of the structure at working loads. Okay, suppose you are living in a building and there are several structural members of that building, like beams, columns, slabs, etc. Okay, so suddenly you realize that your beam has started to deflect like this. Okay, or you start to see the cracks in the beam like this. Okay, so your structure, it might be safe in strength. Okay, it will not collapse suddenly, but what happens when you start to detect such type of problems in your structural members uh, where you are living? So you would definitely not like to stay in that house anymore. Okay, so what happens, limit state of serviceability says that your structure should be serviceable during its lifetime for the working loads. Okay, so here we are going to discuss about the control for deflection. Okay, so let us start it. So here I have written, so what is your control for deflection? It is as per IS 456-2000. So clause number 23.2. Okay, clause number 23.2, it deals with your control for deflection. Okay, there is also one annexure which is related to your deflection control, and that is annexure C of Indian Standard Code, and it takes into account the value of long-term creep. Okay, so deflection due to long-term creep. Okay, so but in simple terms, when you are going to design slabs and beams, we are going to check its deflection under clause number 23.2. so here we are going to discuss clause number 23.2. okay, so deflection of a structure or a part shall not adversely affect the appearance or efficiency of the structure. Like I said, that if you are living in a house, okay, so in that house you suddenly realize that the beam of your room or your house has started to give cracks. Okay, or it has suddenly start to deflect. Okay, so that is not desirable. Okay, so it will adversely affect your appearance as well as the efficiency of the structure in future. Okay, so we need to check the structure for deflection first. Okay, so here we are going to discuss about the deflection control for beams and slabs first. Okay, so for beams, when you design a beam, we check the deflection for first point is when you are designing a beam up to span of 10 meter. Okay, so first of all we will check the span to effective depth ratio. Okay, span to your effective depth ratio for your cantilever section. The span to effective depth ratio should come about 7. Okay, and for your simply supported, this span to effective depth ratio should come out to be 20, and for continuous beam it should be 26. Okay, so we need to check the deflection control. The deflection depends upon the span. Okay, so suppose this is the beam section. Okay, and these are the supports. Okay, so when this span goes on increasing, okay, when the span goes on increasing like this, the deflection will be more. Okay, so your deflection directly depends upon the span. Okay, and span and your effective depth of the section. So in case of your cantilever, we check it. In case of your beams and slabs, first of all we check the design section for your span to effective depth ratio. Okay, if span exceeds 10 meter, then above values should be multiplied to 10 by span in meters, except for your cantilever section, for which your detailed analysis is mandatory. Okay, this is given in your IS code 20 clause number 23.2. okay, you can check it from there also. So what we need to do, we need to now multiply these values. If the span exceeds 10 meter, then these values should be multiplied with a factor which is 10 to span. Okay, another thing that we need to take into account while checking for deflection, so we need to take a factor which is called modification factor. Okay, taking your tension and compression steel into account. Okay, so the values which are mentioned above. Okay, so these values should be multiplied by a factor which is called modification factor. Okay, so I'm again saying the values which are given above in point number 1, they should be multiplied by 10 to span in meters when the span exceeds 10 meter. Also this value will be multiplied by a factor which is called modification factor, taking into account the tension and compression steel. Okay, so these are the points that we should take into account while checking for deflection. Okay, now we'll see here this your modification factor, which is K. It can be found out by using your figure number 4 and figure number 5 of Indian Standard 2000. Okay, IS 2000 at page number 38 and 39. These figures, figure number 4 and figure number 5. Okay, so this figure number 4 is for tensile steel. Okay, and this figure number 5 is for compression steel. Okay, this is for compression. So here I'll show you in a book for reference this table. This table is figure number 4. Okay, this is the modification factor for tension reinforcement. Okay, so you can see here this is your modification factor. Okay, and this is your percentage tension reinforcement. Okay, and these are certain values which are written here. This is your Fs. Okay, so now I am going to tell you what this Fs is. Okay, so this Fs is calculated as 0.58 Fy, area of cross section of steel required divided by area of cross section of steel provided. Okay, so we check first of all we calculate the value of Fs. Okay, so this Fs, what is this Fs? This is the stress. Okay, this is the stress of service loads. Okay, in simple terms, so we need to calculate this stress for loads. Okay, this is given by your 0.58 of Fy, area of cross section of steel required, to the area of cross section of steel provided. Since when we design the structure, at first we don't know the value of percentage of steel while just starting the problem. Okay, so we need to assume that value. Okay, so to start with, this value of Fs, it is taken equal to 0.58 Fy. Okay, so for your Fe 500, okay, we'll calculate first of all Fs. It will be 0.58 multiplied by 500, 290 Newton per mm square. This is for your Fe 500. So now we'll calculate it for Fe 415. Fs will be 240 Newton per mm square, and for Fe 250 the value of Fs is 145 Newton per mm square. Okay, so now what is this factor? This factor 0.58 Fy. It is derived as Fs equal to Fy divided by 1.5 multiplied by 1.15. This is factor of safety for loads, and this is factor of safety for steel. Okay, that's how we get this value, that is 0.58 of Fy. Okay, so now look here. We have calculated these values. As for your Fe 500, we have calculated this as 290. Okay, and for your Fe 415, the value is 240, and then the value is we have calculated another value, that is for Fe 250, the value is 145. Hence we have drawn the curve like this here in this graph. Okay, so we have the standard values of your steel stresses, which are given in this your graph. Okay, so in this from this figure, we can now calculate the value of modification factor. This modification factor depends upon the percentage of tension reinforcement. Okay, so as I told you that initially your PT, what is PT? PT is the percentage of steel. Okay, it is represented by PT. So if initially your PT is not known, so first of all we need to assume the initial value of PT. Okay, and find the modification factor by using the figure. And since it is desirable to use your under reinforced section every time, okay, so PT should be assumed as, how to assume this? It is assumed as 40 to 50% of PT limiting. Okay, what is this PT limiting? PT limiting is your limiting percentage of steel. Okay, for mild steel, 40 to 50% of your limiting percentage of steel for mild steel, and 30% of your limiting percentage for HYSD bars. This is the value that you need to assume at the start of the design. Okay, and to decide your modification factor, the value of your modification factor. Okay, so finally when the beam has been designed, when you will design the whole beam, okay, when the beam has been designed completely, the required PT is known. Now we after designing we will know what is the tensile steel we have provided in the design. Okay, so AST required and AST provided will also be known, so hence we can compute Fs. Okay, now for this value we can calculate the value of Fs. So how we are going to calculate? We are just going to use this table or figure. This figure is given in your IS code at page number 38 and 39. Okay, this is this table which is given here. This is the this is for modification factor for tension reinforcement, and another table which is given here is here, you can see here, this is the percentage compression reinforcement table. Okay, and the value of modification factor. So you can take the value from this, from here. Okay, so now after knowing the percentage of the steel, we are going to calculate the value of your Fs by using this formula which I have written here, that is Fs equal to 0.58 Fy. Now area of cross section of steel required, okay, this is known, and area of cross section of steel provided, this is also known. So you can check the value of your modification factor. Okay, so now alternatively you can calculate the value of K by using an equation which is your 1 divided by 0.225 plus 0.00322 Fs plus 0.625 log to the base 10 Pt. This is percentage of steel. Okay, and Pt is given by 100 AST over Bd. So either you can calculate the value of this modification from this table, okay, or you can take the value from this equation. Okay, so now in case of slab, Spanning in two direction. These are the values for your one-way slab as well as for your beam sections. But in case of your slab spanning in two directions, okay, that is called two-way slab. Okay, so the shorter span will be considered for the calculation of span to effective depth ratio. As we know that we need to, for deflection control, we need to check the first of all the value of your span to effective depth ratio. Okay, so span to effective depth ratio in case of your two-way slab, two direction. Okay, the two-way slab, the shorter span will be considered for your calculation. The span you are going to use is your short span. Okay, then you are going to check the values. Okay, so but there is another one more thing you need to take into account. So that is for two-way slabs, if your shorter span is up to 3.5 meter, okay, and your reinforcement and it is reinforced with mild steel bars along with the loading class up to 3 kilonewton per meter square. Okay, so the following values should be adopted. Okay, so that is a span to effective depth ratio. The values will be modified. Okay, the values that we have taken, that is 7 for cantilever, 20 for your simply supported, 26 for your continuous. So here what we are going to use the values, we are going to use for simply supported slab 35, and for continuous slab we are going to use 40, this value. Okay, for HYSD bars, if the bars if these values are for mild steel bars, but for HYSD bars we will multiply the above value by a factor, that is 0.8. Okay, so these are the some points that we need to take into account. Okay, so another thing is there that the final deflection due to all possible types of the loading, this is given in clause number your clause number 23.2. you will find it. Okay, in your at page number 30, I said then that at page number your 38. Okay, you will find these values what I am discussing here. The final deflection due to all possible types of loading due to creep, shrinkage and temperature etc should not be greater than span to 250. Okay, this is a very much important. The overall deflection within the structure should not be greater than span to 250. Okay, so and another one is that deflection including effective temperature, creep, shrinkage occurs in shrinkage occurring in your erection of partition and application of your finishes. It should be restricted to span to 350 or 20 mm. This is also given in the code. Okay, so here I have written. Okay, so the deflection including effect of your temperature creep, shrinkage occurring after erection of partition and application of your finishes should be restricted to span to 350 or 20 mm, whichever is less. So these are the control for deflections for overall deflection in the structure. So if when we take into account your creep, shrinkage, so these all values are discussed in annexure C of your IS code 456/2000. Okay, so this is all about your deflection in the slab. But this is how we check the control for deflection, and this is very much important as per the requirements of your limit state of serviceability. Okay, so now let us take example on this. Okay, I'll discuss an example here. So we are provided with a simply supported RCC rectangular beam of B by D size as 200 mm. This is the width and this is the overall depth of the beam. It is reinforced with two 12 mm bars and 3 16 mm bars as compression and tensile reinforcement. So the steel required to resist the load is 563 mm square. Use M25 and Fe415 steel. Now check deflection of the beam if length of the beam is 5 meter, okay, and effective depth is 250 mm. So this is the problem. So in the given problem, we are provided with your width of the beam is 200 mm and overall depth is 300 mm. So if this is the beam section, so this is your 200 mm and the overall depth, this is the overall depth, okay, so this is your 300 mm, okay, and we are provided with also the effective depth. Okay, effective depth, what will be the effective depth if this is your reinforcement which is provided here, okay, so the effective depth will be from here top the reinforcement to the center of your tensile reinforcement. This will be your effective depth, okay, so this is given as 250 mm, okay, so we are provided with this. So in this section we are provided with also compression steel, okay, so this is your problem here, okay. So now AST provided, okay, so AST provided, we will calculate first of all the AST provided. So 3 bars of your 16 mm dia, so we'll calculate the area, that will come out to be 60318 mm square. Now AST required, this is given, okay, this is given in the problem. So this is 563 mm square, this is the required area of the steel, okay. So this is your tensile steel we are talking about here, okay. So we have provided 3 tensile bars of 16 mm dia, these are 3 bars, okay, so here will be 3 bars. So and now ASC provided, so we have provided compression bars, 2 bars of 12 mm dia. So we'll calculate the area of steel in the compression, that is coming out to be 226.20 mm square, okay, clear. Now we'll calculate the percentage of steel in tension, okay, so this is the amount of the steel, that is 603.18 mm square provided, steel provided, divided by AST divided by B into D, okay. So we multiply by 100, that will give you the percentage. So it is coming out to be 1.206%. This is the percentage of tensile steel. Now we'll calculate the percentage of your compression steel. This is the ASC, that is compression reinforcement, B into D, multiply by 100, it is coming out to be 0.452%, okay. This is your percentage of compression steel. Now next we need to calculate the modification factor here. So now the modification factor for your tensile steel, first of all, that is K1, okay, for which we need to first of all calculate the value of Fs. So Fs is your 0.58 Fy AST required divided by AST provided. So we'll calculate 0.58, 415 is the value of Fy. AST provided, AST required is 563, provided is 603.18 mm square, okay. So now we'll calculate the value of Fs. So Fs is coming out to be 224.67 Newton per mm square, okay. Now you can check the value for this Fs by using figure number 4 of Indian Standard 456-2000, okay. So here I'll tell you by using this figure, okay. So we have what is the value of your Fs? Fs is your 224.67, okay. So we'll check here for your Fe 415, the curve is this curve is for your Fe 415, Okay, now what is the value of fs that we need to check from this graph is, that is your that fs is coming out to be 224.67. okay, so the value of this 224 will lie between this 190 curve and 240 curve. Okay, so it will lie in between, somewhere in between the two values. Okay, and so we need to first of all draw the curve by interpolation. Okay, and by interpolating the values, and here the tensile steel that we are getting is 1.2%. okay, so 1.2% is the tensile steel. Okay, so for tensile steel 1.2% and for fs 224.67, we will calculate the value of modification factor. Okay, so the value will be in between somewhere here, and the modification factor will come here somewhere. Okay, so we will calculate that value by interpolation. Okay, so for fes we'll first of all check this curve for 1.2 steel, so it is coming out to be something 1.15 value. Okay, and for fe 240 we will check the value, it is coming out to be your here. Okay, 0.95. okay, so we'll interpolate the value in between. Okay, because we have the difference from 190, because we will calculate the value for 224.67. okay, so we'll calculate by interpolating the values. So 1.15, by using that curve we'll interpolate the value like this: 1.15 minus 1.15 minus 0.95. this is the value for your 190 curve, and for this is the value for your fe 240. so this is for fs 240. okay, so we'll calculate these value by interpolating, by interpolation. Okay, I hope you all know how to interpolate the values, so I'll not go into the details of interpolation here. So we'll get the value as 1.01132. okay, so this is the modification factor that we are getting for tensile steel. Okay, so the value we will take here the value approximately 1. So now the percentage of steel is your 1.206 and fs is your 224.67, and the modification factor is your 1. okay, so similarly for compression steel K2, figure number 5, IS 456 2000, we'll check compression steel is 0.452% and K2 value will be coming out as 1.13. so here I will show you the diagram for your reference. So this is the value. Okay, so for your what was the value of your percentage of steel? It is 0.452. okay, so 0.452 will come out here somewhere here. okay, 452, and for which the value should be like here, from here. okay, so it is coming out to be 1.13. okay, so we have taken it as 1.13. you can exactly interpolate the values by looking at the figure. okay, so now we have both the modification factors. Modification factor for your tensile steel is 1, for compression steel it is 1.13. now basic span to effective depth, now we'll go to the clause number 23.2. so for your simply support, as the given problem is for simply supported, so we'll take the value as 20. okay, so 23.2.1 you will check it from here, and now of IS 456. now we'll multiply this value. The code says that we need to multiply this value by both the modification factors K1 and K2. okay, so we'll multiply the value. 20 into 1 is the one modification factor, and K2 is the another one modification factor, that is 1.13. so we'll get the value as 22.6. this is the modification factor. okay, so this is your basic span to depth ratio that we are providing. Now as per the IS Indian Standard Code. Your span to effective depth ratio should not exceed this. Okay, so now modified span to depth ratio as per your given problem. So we have span of 5 meter, so 5,000 divided by effective depth, that is 250. Okay, span to effective depth we are taking it, so it is coming out to be 20, which is less than 22.6. so hence your structure is safe against what, your deflection. Okay, so this is how we solve the problems. Okay, for control for deflection in your limit state of serviceability requirements.